Alright, what's going on everybody? Today we're going to be doing another LeetCode problem. This one's called largest rectangle in histogram. It's a hard, um, so let's just get into the problem. We're given an array of integers called heights, and it corresponds to the histogram's bar height, where the width of each bar is 1, and they want us to return the area of the largest rectangle in the histogram. So basically, we're given an array of heights in C++. This is given to us as a vector, vector array, potato, tomato. So we have an array of heights and its integers, and we can see that each integer just corresponds to the height of a bar in a histogram, and then each bar is going to have a width of 1. So we're imagining this as being like a 2D graph, basically. It's like a geometry problem. So 2D graph, this bar's got height 2, this bar's got height 1, this bar's got height 5, so on and so forth. And they want us to find the largest rectangle that could geometrically fit into this histogram. So as you can see, they have the output. So the left is kind of just the problem, the right side here is the answer to the problem. And we can see that the largest area rectangle is going to be a 2 by 5, and it's going to have area of 10, and that area is what they want us to return. So you could see that there could also be a rectangle here, like could be a 2 by 4 here. But that's not the max, so we don't care. But we're still considering it. It's just not the answer. There's a 1 by 6 here, just where this bar is to make an area of 6. There's a 1 by 6 down here to make an area of 6. You could also have like a 2 by 2 here. You wouldn't even consider that though in this case, because it's not. You would extend it, and for the algorithm I'm going to show, but nevertheless, another example here, you could see that there could be ties. So the area of this 2 by 2 is also the same as this area of this 1 by 4. They both have an area of 4. But it just wants the max area. It doesn't matter if there's a tie, so you just return 4. So they're just clarifying that there. And then as far as constraints go, your heights array is going to be at least size 1. So there's going to at least be one element there. And then each element has minimum height of 0. So you're not going to have to deal with negative heights or anything like that. So let's just get into the algorithm here. So for the optimal approach to this problem, you're basically going to want to use a stack it's going to be a stack of pairs where the pair is an index and a height, but as you'll see shortly, the index and the height don't necessarily correspond to the same element. You're trying to extend rectangles as much as you can, and then you're storing them in the stack, basically to remember them, and then you're going to be comparing them with each element, or not really comparing them with each element, but you'll see when we get into the algorithm. So we're going to use a stack, and since I've already seen this algorithm, I know that the time complexity is going to be linear. It isn't necessarily going to be have n steps. In the worst case, it could have like maybe 2 n steps, but it's not going to be like n times n steps. So it's definitely linear time. And then the space complexity is going to be linear also, because for this, for sure, we can at most have n elements in our stack. So that's got to be, this one is for sure linear space, just because of the stack. So yeah, let's just get into the code. So I'll scroll back up here so you can see this as we go, but the visualization, that is. So we're gonna have a stack of pairs. Remember, where each the first and second values in the pair are both going to be integers, because the first value is going to correspond to an index, the second value is going to correspond to a height, which are given as integers. So we'll call this st for short. We also need a integer value for the max area that we'll be keeping track of. We'll use that to just keep track of the max area we've seen, and then we'll return that at the end. So that's basically the result. So first order of business here is we're just going to want to iterate over each element and heights. And I'll just use a C-style for loop here. Well, height is less than size. We want to hit every element there, so all the way to the end. Just incrementing I along the way. Now we're gonna want a pointer in here. That's basically gonna point at each iteration to as far as we can extend our rectangle backwards, and we'll use the stack to help us determine how much we can do that. So in left, that'll be our pointer, and then we're also going to want to push at each iteration here in the outer for loop. We're going to want to push into our stack that left pointer and then the height of the current element we're at as a rectangle, essentially. So we're going to push that into the stack at each iteration. And then basically, so what do we do with the stack now? Well, we're basically going to want to check. We're going to want to make sure our stack has elements in it. Otherwise, we don't want to do anything with it, right? Because we don't want to access stuff that doesn't exist, essentially. So while the stack has stuff in it, we want to check, is this element at the top of the stack, is its height, so dot second, is its height greater than the height at the current element we're at in the outer for loop? Now, if this is the case, let me basically just visualize, or not visualize, but try to explain better what's happening here at every iteration of this inner for loop. So say we're moving along our like a histogram that was given as input for, that's okay, because remember, we're checking if the height at the top of the stack is greater than the current element. What does that mean? It means if we get like a 1 here, this current height that we're at, remember, we're pushing this 4 each height into the stack as we go along. So if this 4 is greater than this 1, we're basically saying, okay, well, we can't extend a rectangle of height 4 any more to the right because the height at our current element is lower than that. So we're going to go backwards into our stack and try to basically extend. We're going to simultaneously extend this left pointer as far as we can get it, as well as compute the areas of each of the rectangles that we've already seen so far in the stack, and then consider them for our resulting max area. So let's write the code for that. So we're basically going to need to pop, and noticing a bug here, this should be I. Our left pointer is always going to start at I as we iterate through the outer for loop. So anyways, and then we're basically going to be trying to extend that left pointer backwards. So we need to acquire the top pair from the stack. So to do that, we can just assign it to a pair of integers, just a new pair here. So new pair, we'll call it this, or actually I'll just call it top because it corresponds to the top of the stack. And we're going to assign it to st.top. And then we can just do st.pop because we don't need that pair in the stack anymore. And then we basically, like I said, we want to update the max area here. So that's going to be the max of the current max area, or the width times height calculation for the current rectangle we're considering. Now, what rectangle are we even considering here? Well, it's going to be the height of the current element at the top of our stack. So dot second times, and then the width is going to be, like, let's say you were you added this 5 to the stack, you added this 6 to the stack, then you get to the 2, you see this 2 is less than the 6. Well, basically, to get the area of the rectangle we're considering now, you would take this index here for the rightmost point on the x-axis for the width. So you take this I, subtract it by the index of this rectangle at the top of the stack, which is either going to be, the corresponding actual index of the bar, or it could be a left index that's been pushed already, downwards. So nevertheless, so this is going to be I top dot first, and that'll just give us the area there. So and imaginably, as you slide that left pointer down, you're like, so for the next one, you would pop the 6, and now you'd be considering this 5x2 volume or area 10 rectangle, because you're shifting the left pointer, and then you're maintaining the height of that element at the top of the stack. So nevertheless, that's how you update the area for this part of the algorithm. And then we're going to shift that left pointer along. It's going to correspond to the new, or its new value is going to correspond to the value of the old index on the top of the stack. So top dot, that would be first for the index. So that's pretty much it for this part of the algorithm, but we're not done. There's still going to be potentially rectangles in our stack that we haven't considered for the max area that have a final index of at the end of the heights array. So for example, we'd execute all this code for this case, and we would still have a rectangle, a 1x3 here, starting here. You would also have, and that gets cut off, notice, because this 2 is like, we couldn't extend this rectangle of height 3 any further to the left because this 2 is shorter. But we can have a 4x2 here because we can have one that's height 2 and it just gets cut off here by this 1. And then so that would be, we'd also have a 2x4 of size 8. And then we'd also have, remember, all of these start from this final index. We'd have this 1x6 here that just goes all the way to the end. So the way we consider those in is they're literally going to be stored in our stack exactly as we need them. It's going to have the leftmost index because we updated that in this part of the code, and it's also going to have the height of the last the height is going to correspond to the height of the rectangle we're considering. So that's just the way the code works. Like this 3 will have height of in the stack will correspond to a height of 3, and then an index that is the last element in the stack. Likewise for the rest of the rectangle. So let me just write up the code here so you can see what I'm even talking about. So basically, while our stack isn't empty, and this is really just like a kind of a quirk of the algorithm, so to speak. Like, they're really, but this is just one of the most intuitive ways I've seen of solving this problem. So even though the algorithm's a bit quirky, like it's much easier to understand than like a lot of other methods or a lot of other approaches to this problem. So we basically want to say while the stack isn't empty, so we want to go through all the rectangles that are still in there, and we can go ahead and just grab that top element. So I'll use the same code. And then we're going to want to compute the width. So the width is going to be remember, they're all starting at the last element there. So heights.size minus, and then it's basically just going to be the top, the x coordinate, or sorry, the left pointer that was stored in the stack at that point. So that'll be top dot first. And then finally, we can update the max area or consider it as a potential max area by using the max function, and then just multiplying that with times the height of that rectangle, which is going to be top dot second. So that's pretty much it for the code here for this problem. After that, we'll have looked at we'll have considered every rectangle that could potentially have a maximum area. So let me just look at this for bugs. And let's see, I don't see any, but this algorithm is a little more involved, so I wouldn't be surprised if I made one. Yeah, so I forgot one of those, what is it, greater than brackets, heights. Yes, I meant heights here. Okay, let's see. Push heights, singular again. Great. Okay. All right, accepted 2 milliseconds. So there we go. Again, our time complexity is going to be linear because we're iterating through each element in the array once, and we're not comparing every element with every other element. Like, yes, we're going to have a stack, so it could technically go past linear time, as in, like, the worst case, instead of being in time, might be like 2 in time, but that's still big O of n, still linear. And then for space, we can at most have in elements in our stack, which is going to be linear space. So hopefully this problem helped you, or this video helped you understand this problem more. If it did, please leave a like and subscribe. Looks like we beat 49%. I'm going to run that again because it's not good enough. Beats 52%. Okay, this is I've gotten like 95% plus several times with this similar code, so okay, 81%, I'll live with that. So 81% runtime, 57% space. Anyways, if this video helped you, please leave a like and subscribe, and I'll see you guys in the next. Thanks for stopping by. Peace.